Many of you watching this video already know that RAG is retrieval augmented generation. It's what allows you to query documents by breaking them into chunks and then pulling the relevant chunks into the prompt that you send to a language model so that your answers are grounded. Now, this video is focused on building a RAG pipeline using Postgres as opposed to using a third-party service. And I'll go into the reasons for why you might want to do that. And I'll go step by step through how you set up Postgres and implement a fairly advanced implementation of RAG. Now, I originally stumbled across this approach because I was building using third-party services. I was trying to build an app that had very low latency, so very fast speed in answering questions about my documents. And I found that I was losing a lot of time just making queries to get the embeddings from third-party databases. So I said, why don't I set up a Postgres database on my own server so I can cut out that latency? And it did shrink the time a lot and make my responses faster. Now, I wasn't too sure that was something that was more widely used until I went to an AI meetup just recently, and Steve Pusty was giving a talk on exactly this topic, which was using Postgres to build retrieval systems. And it turns out I had used some of the key tricks that allow you to get speed, namely PG vector, and there's another trick called PG best match that I'm going to talk about today. In any case, this is a fairly advanced tutorial on how to set up a database. It will work if you're going to use a third-party LLM, but it'll also work if you're going to run a local LLM for a more private setup. I will try and explain some of the basic terms, so if it's your first time doing retrieval augmented generation, you should also have a shot at being able to get something up and running by yourself. And interestingly, Postgres was developed, it's back in the 80s now, so it's been around quite a while, but it was developed at UC Berkeley, just as VLLM was. If you're familiar with that inference library, I've made a few videos on it as well, but that's something more recent. Just interesting that there's a lot of high quality open source coming out of UC Berkeley. So here's the video structure. I'm going to talk through what RAG is used for. I'll actually show you that app I mentioned in the intro because it'll give you a sense of what you can achieve by the end of this video if you go through what I do step by step. I'll talk then about why Postgres as opposed to using a third-party service, give you some of the advantages there. Then I want to describe a little why you would use vectors and text for doing a search for the most relevant chunks. Then I'll give you a little bit of chat on PG vector and PG best match. These are capabilities within Postgres that really speed up getting the best chunks. And then, even though it looks like it's just 5 and 6, most of the video will be spent on these two last points. The first being a basic Postgres RAG implementation. I'll more or less just use SQL queries here. And I've put this in a free repo that I'll show you later called Basic Inference. And then I'll walk through, it'll take me more time, a more advanced implementation that allows you to scale up to parallel requests and includes some other tricks to improve the quality of your retrieval. And that's available in the Advanced Inference repository. Let me just show you that app. And you can actually take a look at the demo yourself. If you go to assistant.trelis.com, you can just put in your email and log in. There's free credits for the demo, so you can try it out. But in the first step, you'll upload some documents. I've uploaded here some touch rugby rules, and that is going to be split into chunks. Those chunks will be embedded and they will be sent to the Postgres database. They will be recorded as vectors generated using neural network, but they'll also be recorded. We'll record what's called BM25 statistics, which allow us to do a fancy form of keyword search. And those two methods will be combined then to find the most relevant chunks. So once you have uploaded your documents, you can then go and query. And behind the scenes here, which we'll be going through today, I'm doing a search using the dense embeddings, namely the neural net embeddings, and also the sparse or the text type search. So let's just ask a quick question here and say, how much is a try worth in touch rugby? And in this speed approach, I'm using one of the very fast LLMs to give a response. So you can see the response is nearly instantaneous because I'm not only using a Postgres database that's on my server, so I'm losing very little time for doing the vector search, but I'm also then using a very fast LLM. I'm using Cerebras. I think I had used Groq for a while. You could use Groq or Cerebras to get very fast responses. Actually, as a tip, you can also use Llama 8B, for example, or you could use Gemini 8B. Those are very fast models you need to find a fast serve of Llama 8B. Actually, the Fireworks serve is reasonably fast, maybe Together AI as well, but you can use those if you want to get very fast responses too. This is ultimately what we're going to build, but what we're going to build is the back end where we split up the documents, we do the search, we pull those search chunks back so that we could send them to a language model. And I should mention, by the way, you'll see that there's citation verification here as well. So I have actually done a search within the text to see that this chunk actually appears in the test and is not hallucinated. You can check that out in a separate video on citation verification if you're interested. I'm not going to cover that today. It's an added feature. But let's talk about why use Postgres as opposed to using some third-party service. And in short, I'd say it's cheaper. It's cheaper because you don't have to pay for the third-party service. You can literally run Postgres on your own server, or you could run a separate server for Postgres. It's faster. There's no delay in querying a third-party server, so you just save on that latency. And you can also get the search itself within the database very fast by using the functions I'll show you today. And last of all, it's customizable. So you're able to do specific setups, for example, like the one today that I recommend, where you combine a sparse search with a dense search and you use the best of the chunks from each of those methods. Now, you can often do these kinds of hybrid searches using third-party products too, but I find if you want to customize a bit, maybe customization doesn't matter to you, but if it does, then it's probably easier if you've got your own implementation. Now to the question of why use this joint search? Why not just use vector embeddings and rely on that solely? And the answer is because they each serve a different purpose and they search for the relevant chunks in a different way. Vector search is good for meaning search. I'll give an example, whereas text is good for exact word type matches. And actually, we can extend to fuzzy matches as well for this form of text search. And I'll talk a bit about that later on when we get to the advanced section and techniques like normalization and lemmatization. So if you just use vectors or embeddings, which is another word for vectors, you're going to miss a lot of the relevant document chunks. If you just use text search, you also might miss some chunks because it's not going to be able to capture meaning when the words are different. Now, I do have a video, which I've linked here. If you want to check it out, comparing vector versus text performance, I go through a worked example where I show how the performance compares. And I'm not going to go through the full example there, but I think it's worth showing you the results. Here on the x-axis, I've got the percentage of relevant chunks that were accurately retrieved. Higher is better in this case for retrieval performance as we move to the right. And I'm comparing three different techniques: BM25, which is a text search, similarity, which is the vector or embedding search, and then combined. So in the similarity, I take the best three chunks and see if I've got the right one. BM25, I take the best three using text search, see if I've got the right one. And combined means I consider the top three from similarity and from BM25 and see if I've got the correct one. And I've actually done the same thing, but using top 12 instead of top 3 up here for these examples. And what you can see is that actually BM25, in many cases, when you've got a low number of chunks particularly, it can outperform if you just do this BM25 text search versus doing similarity on its own. And then if you combine both of them together, you get the best performance because you're adding two slightly orthogonal techniques. So for best performance, I would recommend you do both and take the top chunks from each. Now, in the case here where I have 12 chunks, I've got so many chunks, I'm increasing my chances of having the right one. And I've actually got all of the correct chunks for all of the questions here in the combined case and in the similarity case, whereas I've dropped back a bit on BM25. Depending on your use case, you may find using similarity alone versus BM25 alone is better or worse. But typically they're slightly orthogonal or even quite a bit orthogonal, so they can complement each other. And by using both, you get better performance. Just to give very quick examples, in a vector search, what you're doing fundamentally is representing the query as a vector. So you're saying, here's, let's say, a keyword in my database, dog, and dog is represented by this vector. Here's another piece of text in my database, apricots are a type of fruit. And that's represented in meaning space, which is a very high dimensional space, by that second vector. And so when I ask a question, whose dog, that also will be represented by a vector. But because these two are closer in meaning, the vectors will tend to be closer. And so we will deem this one dog to be more relevant because the angle between these two vectors is closer. So the way to think about meaning search is meaning is represented by a vector pointing a certain direction. We have a database containing chunks from our documents. This is a very short chunk dog. Here's another chunk here. And when we ask a question, we're going to grab the chunks that are closest to the question in meaning space. Now, where vector search is good then is if we ask a question like, how is the main character feeling? And there's a chunk in the text that says the young man was feeling hopeful. That's going to do well. Now it'll do well in text search as well because I've got the word feeling. But if I just take that out and I said the young man was hopeful, probably there's still a good chance this will be found by vector search because hopeful is a feeling, so it'll have some similar direction to the word feeling up here. Meanwhile, text search is going to be good for exact matches or near exact matches if you use more advanced techniques, like what is the price of receipt with this random letters as a code, and then you'll find a chunk in the database that has that same code. And the problem here with vector search is that if you're relying on just this match here, but your query is really long and it's just got this small bit of a match, this word, if you can call it that, is going to contribute too little to the direction of the vector. And so these two vectors won't necessarily be pointing very closely in the same direction if this specific word represents a very small portion of the total meaning. So as a side note here, how is it that we rank chunks according to text search? We don't just take every single word in the query and then look for all of the chunks that have those words. That would result in us finding far too many chunks. So we need to be more discriminatory when we do a text-based search. And the way we do that is we first split the query into keywords. So we've got the keywords here. Often we might just keep the words with the words that have 3 letters or more or 4 letters or more. And then for each one of those words, we find chunks where the query keywords, namely these, are both frequent in the chunk and also rare in other chunks. And there's a reason for that. The intuition is that if we find a query keyword that's frequent in a chunk, so you can imagine a newspaper page and it very often has the word carnival. If carnival isn't the query and it's now in that newspaper page many times, that means it's more likely that page is going to be relevant. However, if the word carnival is on every single of the newspaper pages, that doesn't help us distinguish a lot. So you can see we need a combination of the keywords in the query being frequent in a given page, but not frequent in the other page. And this is ultimately the formula that BM25 accomplishes. It's a measure of high frequency in a given chunk relative to lower frequencies in the other chunks for that query keyword. And if you go to an advanced BM25 method, you're often able to set a parameter that includes length normalization. So you can normalize to some degree the effect that longer newspaper pages, they will naturally have a tendency to have a given word in it more often just because it's longer. But if you have documents of different length, you often want to normalize that out, and you can control that via normalization in one of the advanced BM25 parameters. So very roughly, BM25 is just keyword search, but it's not just pure keyword search, because that would result, if you do Control F on a PDF, you're going to find way too many pages. So to be more discriminatory, you have to look also at the relative frequencies. Okay, so that's why we're going to use vector and text search. And I think there's one more comment I want to make on vector search, which might come up in the advanced section. I think I'll just say it now. Sorry, it's right here. How do you combine them? We can just do vector search. We can just do BM25. One way you can combine them, which is often called hybrid, means you just combine the two scores in a weighted fraction. So you'll have some value, maybe alpha, that will weight the vector score versus the keyword score, the BM25 score, and give you an overall score. But I would warn that this is not robust in many cases, and it can result in all of your chunks just coming from one method or the other. And that's because even if you optimize your weighting, there's no particular reason that the normalization of your BM25 and of your embeddings is going to match up in a way that they're evenly distributed in a similar pattern. And so what you'll find is most queries, they might tend to just give you all of your chunks from the BM25 or all of your chunks from the embeddings. So you don't benefit from adding in the two types of information. And the easy fix I see to this is don't try and combine them into one score. Instead, just take the top 3 or the top 6. I would recommend either top 6 actually or top 12 from each of the methods and include all of those chunks within your prompt. The language models today, they have large context. All of them pretty much have above 4,000 context, and many, like OpenAI's models, are 100K, Claude is 200K, Gemini is 1 million. So there's no problem with putting in more chunks, and they're capable from a reasoning perspective as well from throwing out the bad ones. I think it's more robust just include the top K from each of the methods rather than trying to combine them into some hybrid score, which I see done fairly often. So let's now talk about Postgres tools. And these tools are really key to making Postgres a reasonable choice or a decent choice for doing database search. If we didn't have these tools I'm going to talk about, then yes, it might be a lot faster to use third-party services. Now, by the way, many third-party services will, in any case, use Postgres and these types of techniques. So it'll be useful for me to describe them anyway. Now, there's actually one technique for each of the searches. So PG Vector, actually, that's not quite right. PG Vector is basically an extension you can add to Postgres. Let me show you here. And this extension allows Postgres to handle vector search very fast. And because we represent embeddings as vectors, PG Vector is what makes the embedding search fast. It's actually also used in PG Best Match. So PG Best Match is a way to do keyword search using vectors. That's what it is. And how does it do that? It creates a sparse vector, and I'll tell you why it's sparse, for each query, or rather for each chunk in the document. And then when you are at inference time, you will create a sparse vector for the query, and you'll use vector search actually to find the closest vector to give you the chunk that is closest. And it's equivalent basically to a BM. It is equivalent to a BM25 search. Now, why is it a sparse vector? It's sparse because based on all your documents, you're going to come up with effectively a dictionary of all the keywords. So you'll have a dictionary of all the keywords, and then you're going to measure the occurrence, the frequency of each of those keywords in each of the chunks in your document. And then you're going to compute the relative frequencies, the inverse frequencies. These are the key statistics for BM25, and you're going to store them. You're going to store them for each of the chunks. And then at inference time, you'll compute the statistics for the query. And now effectively what you have is a vector for each chunk and a vector for the query, and you can just compare them using vector search. Now, why is vector search beneficial? Like, what else would you use if you're not using vector search? You could do just literal brute force comparison. If you have the word dog in your query, you could just brute force compare that to all of the words within your database that looks at all the files. Now, that's called brute force for a reason, because you literally have to run all of those comparisons. But here's where vector search is useful. With vector search, you've got a vector or a direction for the query, and you have a whole host of vectors that represent the document. But what you do is, before you run any query, you have your database sorted, and you sort it out so that the vectors are organized into clusters. And you can do this hierarchically, which is called hierarchical small world. But by setting up clusters, you can think of it as, okay, here's a few vectors from each of the top 3 clusters. Then within each of the top 3, we're going to have 3 more. And then within each of those, we'll select 3 more vectors close to that. Basically, when you do the vector search, you don't have to compare the vector to all the vectors. You just compare initially to the key vector from the 3 main groups. Then you zoom in, you compare to the next ones, you zoom in. So you're able to do far fewer comparisons with vector search. And you can get on an approximate, although really it tends to be quite accurate basis, to your target vectors much more quickly with fewer comparisons. So that's why vector search is a lot faster. And if you can make the problem a vector search problem, you're going to get a lot of speed up. And naturally, doing embeddings is already a vector problem, so you just need a good vector extension package. But for keyword search, PG Best Match is what allows you to make the problem a vector problem and get some speed up in doing that best match. All right, so we're ready now, and we'll go through a basic RAG implementation. This is available in the the basic inference repo. It's a new basic repo I've created, so you can check it out here, Trelis Research Basic Inference. And once I go through that, I'm going to then move and show you the advanced inference repository, which will show you some of the more advanced techniques And I will come back to the PowerPoint presentation first and show you a few of those advanced techniques before I dive into the code. But first, let's just go through a first time how to build the database in a simple way, and then we'll come back for more. So here's the basic inference repository. You can find it on GitHub under Trelis Research. This is a public repo, and I'm going to go through these scripts, and then I'll go through a more advanced version, which are available in the advanced inference repo. This has many, many more scripts from my previous videos as well, and I'll have a more complete and advanced version of the retrieval system we built today. Now, if you are interested in that, you can purchase lifetime access over at trelis.com. I've just updated the website actually, and you can find a section here on deployment or inference and learn more by clicking there on that button to find a full list of the scripts available in this single repo. So I've git cloned the repo into Cursor or VS Code 2 is fine. And let's take a look at the README. So we're going to work top to bottom here, and we're going to start by installing Postgres. I recommend using Homebrew if you're on Mac. So install Postgres and then start the service. You'll also need to install Rust because this is needed for the PG Best Match extension we'll use for BM25. Now these are the commands for Ubuntu. If you need to install on a Windows machine, just put these into ChatGPT and find the instructions for your machine. Now, once we've Postgres installed, we need to install the extensions. There are two to install. The first is PG Vector. You'll move into a temporary folder, clone, move into the directory and make an install. And for PG Best Match, this is installed via Rust using Cargo, which is a package manager for Rust. And actually first we need to install Cargo PGRX, which is going to be used to do the installation. So you're going to make sure that you have Cargo PGRX, or make sure you have PGRX using Cargo, then you're going to install PG Best Match. Now that we have Postgres installed, we can set up the database. I'll just drop the database so I can start off from clean. So let me run this here and create a fresh one, create a fresh user and assign a password. Now I've hard coded a password. This isn't secure. You should use your own password, probably from an environment variables file. Now we'll enable the two extensions. So PG Vector, which is called Vector, and PG Best Match for BM25. And additionally, we're going to set the search path for BM25. We're going to set it to the public or BM catalog folders. BM catalog is created by the PG Best Match extension. Oops, I reran the same thing twice. So next, we're going to create some content in the database. And then we're going to create dense embeddings or embeddings using a vector model. And we'll do a search, which will be semantic or meaning-based search. And then I'll move to the sparse embeddings. So that'll be the keyword-based search using BM25. For all of this, we're going to need to install some packages. So I'm going to make these installations here. Notice that we'll use Hugging Face Hub to download a model for the embeddings. NumPy, we'll use the NumPy library. PG Vector needs to be installed. PsychoPG2, this is for connecting to the database. Sentence Transformers is for loading the embedding model and doing the embeddings. HF Transfer is for fast weight download. And I think INOPS is needed as part of supporting the Sentence Transformers library. So everything's installed here. I'm using UV instead of pip. It's much, much faster. And with that, we can generate some initial content and we can create embeddings for that content. And I'm going to show you what's in that script. So let's just go to generate doc embeddings. When we run it from main, it will run setup demo data, and setup demo data creates a table, inserts text, calculates embeddings and adds the embeddings. So here are the texts, just some different things about different cities. The embeddings will be created by calling get embeddings on the text. And then we're going to create a table. We'll drop the table if it already exists. It's going to have column for the ID, one for the text content, and one for the embedding vector. Now, you do have to define the size of the vector. If you ever need to change your model to an embedding model with different dimensions, you'll need to create a new column. You can't just use the same column. And with the table created, we'll insert the content and we'll insert the embeddings. Just take a look now at that get embeddings function. What it does is load the model using Sentence Transformers, the Nomic AI model, which we'll look at in a second. Then it's going to encode the text from the text into embeddings. And I do normalization. This is actually unnecessary because the vectors are already normalized by nomic, but could be necessary if you weren't using normalized vectors. It may also not be recommended. So you have to be careful on the model you're using and check how they recommend using the model, whether it's with cosine or with dot product. So this was our function to get embeddings. And that rounds out this script, which creates a database. It creates a table in the database, adds text, adds embeddings. And when I've run that, you'll see it takes a few tens of seconds because we have to download the model. We add in the texts. You see they're normalized to unit length. And then we have embeddings of size 768 for each of the 4 texts. And that's all written into the database. Now we can take a look at the nomic model. If I just search for that string. I like this model for 2 reasons. One is it supports embeddings of up to 8,000 tokens in length. That means I can embed complete PDF pages. I like that because I like to have chunks that match each page. It means that when I retrieve chunks, I've got whole pages, and this is easy to reference in the UI and tell the customer, oh, we were referencing this page or that page, rather than having things split kind of by random chunks. The other reason I like this is because you can use the API from nomic if you go to Atlas and query to get embeddings, but you can also run it locally, which is what I'm doing now. So you have this interchangeability, which is nice, and you wouldn't have with, say, OpenAI embeddings, or if you have like mini LM, there's a mini LM type model you can use, which is good to run locally, but there may not be many companies serving that model. And it's nice to have the option of doing API or doing the model locally. So we have a database. It's got the embeddings for documents, and now we want to search. We want to define a query and search for the most relevant documents. Now, before doing that, we're going to index, which is kind of like sorting, the column of the dense embeddings. We're actually going to use a special type of index called HNSW. That's hierarchical navigable small world. And it's a clustering approach whereby it takes your dense embeddings like the arrows, and it will set up a group of clusters. And within each cluster, it will set up clusters. And so when you do a search, you don't actually compare your query to all of the vector rows brute force. What you do is you can find the closest cluster. Then within the cluster, you go down and find the closest cluster, etc., until you find the closest vector. Now, it is slightly approximate because the performance depends on the quality of the clustering. If you accidentally miss a vector because it's just outside a cluster, it means you might find the second closest vector. So it is a kind of speed accuracy trade-off thing, but generally works well for dense embeddings. All right, so we're ready now to do a query, and we'll do that using the query embedding script. When we call this from main, it's going to print out the query, and then it's going to run a search and print out the results. And if you look at the search documents function, it's going to get the query embedding. Then it's going to connect to the database, and it's going to run cosine similarity. Now, cosine similarity is 1 minus the distance. So cosine distance you can think of as the angle between 2 vectors, and it's achieved by using this operator here. This is the cosine distance operator. And because vectors are more similar, if the distance is small, that means similarity is 1 minus the cosine distance. So we're going to look for vectors that are closest based on similarity and return the closest 4. And then those results will be returned and printed out here. Now, just one note, when we run the embedding, there's actually specific syntax that needs to be followed for the nomic model. If you scroll down, you'll see that when we embed a document, you need to add this prefix here, whereas when you add a query, when you do a query, you need to add this prefix here. And that's why when I call the getQueryEmbedding function like this, it's actually using a prefix of search query, and this is being prefixed on, and that's why we're passing in the prefix text when we try and encode it to get the embeddings. So this allows us to do a query and find the most relevant chunks based on meaning or based on semantic search. You can see the query is Paris, and you can see the most similar chunk is Paris is known for the Eiffel Tower. The next is Paris, the capital of France is Paris. The next is Tokyo sushi. The next is Japan and Tokyo. So this all makes sense. So we're at a point now where we've got the dense search completed, and we're now going to move on to doing sparse search using keyword or advanced keyword or BM25 type search. Now, the way BM25 works is by creating an index for each of the documents. So each of the rows in our table, which corresponds to a document, is going to require us to have a dictionary. And the dictionary will be a list of all of the words that are in that document and the statistics for each of those words. So let's try and set up the statistics for each document. And we'll do so by connecting to the database. So we're connecting with to Postgres. And just to be sure, we'll set the search path for statistics to public and BM catalog. This here is created when we initiate the extension via PG best match. Now, just to start from scratch, I'm going to drop the table for the BM25 content and start from scratch with creating a new index using this function from the PG best match library, which will create statistics for the table called documents, and it will create statistics on the column called content, which is our text content, and it will name those statistics document content BM25. And anytime we want to refresh the statistics, which we should do after adding data, we can just call this refresh function. Now, the way we store using PG best match, the way we store the statistics is actually in vector format, where each dimension of the vector corresponds to a term in the dictionary for that row. So we do that using, again, this function that is coming from the PG best match library. And what it does is it takes in this documents content, it creates documents content BM25 using the contents in the content column, which is the text. And it's going to create the data in a format of PG vector. So it'll create these dense vectors. Now, these dense vectors, which I said correspond to a dictionary for that document, a lot of the dictionary entries will just be 0 or empty because a given document is not going to contain every single word in the dictionary. So we can compress all that by dropping the empty entries and making what we call a sparse vector, which will just contain the dictionary entries for the words that are present within that given document. So here we're going to update the documents. I'll just make sure we're starting fresh. So I'll run all these commands. And now we've got a column that is a sparse vector representing the dictionary for each document. And when I say the dictionary, I mean a dictionary of statistics. So each term has got a statistic around its frequency that we're going to use then to determine its relevance when we make a query. So here I'm just going to do a check that we do indeed have this column added. And indeed for each piece of content, we do have this vector created and it looks in order. Now, when we have a query, and I'm going to just create a simple 3-word query, Paris, capital France, we can inspect what that query looks like, also in vector format with the help of BM25 query to sparse vector. So this is another helper from PG best match. And if we run it, we can see that for this query of 3 words, we have this sparse vector here, which is 3 entries. It's got an entry number 4, so dictionary item number 4, number 8, and number 13. And it has a total dictionary with 17 words. And that's because when we created the documents we added in, if you look across all documents, there are apparently 17 words here being defined. And by the way, they're being defined using the BERT uncased tokenizer. It's a tokenizer with a vocabulary of over 30,000. And that's what's deciding what is a word or not within the body of text we input. So here we are. We've got the statistics for the documents now saved to the database, and we have a way of creating a vector for doing search on the query that is. So now if we have a query like Paris, capital France, we can get the sparse vector and use that sparse vector to find the closest entries within the database. Oops. Let's just run that again. And you can see for this query here of Paris, the closest match is this sentence, the capital of France is Paris. And then quite a bit down is the capital of Japan is Tokyo. And then way down is Paris is known for the Eiffel Tower. And then Tokyo is famous for sushi, which has got 0 score in terms of BM25 match. So now we have a working implementation of this best match 25 algorithm. And I'll note here that the way we compare the query vector with the document vector is using the inner product And the inner product just multiplies the terms that match. It multiplies the statistic rather for each term in the dictionary. It's essentially checking the overlay between the document statistics and the query itself. And the higher the overlay, the better. So the higher the best match, the closer we think the chunk is in being relevant to the query. Now, there are a few points I'm going to add on here that I'll deal with when I go through the advanced script, but you'll see already how they're relevant from the basic script. Just to recap, we use the nomic model to create embeddings. Don't forget to add in the prefixes. For dense searches, we use the cosine operator. That's because the model was trained using cosine similarity. For sparse searches, we use the inner product between the sparse vectors, which represent term statistic dictionaries or dictionaries of term statistics. And lower distance. I think this term here is a bit misleading, so I'll remove that. Actually, when you run, I've just clarified that because it was a bit confusing what I'd written, but when you run the inner product using pgvector, it actually calculates the negative product, which is why you have to multiply by -1 if you want to get positive values. The reason for this is because of how it makes it more amenable to indexing, because the sorting direction is more aligned with typical indexes. So that's why pgvector uses negative dot product, but we want positive, just maybe it's a bit more intuitive. So you can multiply by -1 right there. Just to note that we have added an index. So we've used the type of sorting, hierarchical sorting, when we did dense search, but we are not using an index for the sparse search or the BM25. This is a drawback because it means it will be slower when we need to do a BM25 search on a large number of documents. Now, the reason we don't use an index is because this dictionary of terms is actually very sparse. So every document has got different keywords. There's not a lot of overlap, and that means there aren't obvious clusters. And if there aren't obvious clusters, then you can't use this clustering approach to speed up your search as effectively. Or if you do, you might end up just finding the second or third or fifth closest vector. So you lose accuracy basically. Now, in that case, the approach that should be taken is to use a sorting mechanism called IVF flat. IVF flat will create groups based on common dictionary terms. So for a given term, it will just create a dictionary of all of the available documents with that term present in it. That's an oversimplified description. And that's a good approach. But unfortunately, we're not able to use IVF flat on sparse vectors. It's just not supported by pgvector. It is supported by the Rust implementation of pgvector, which is called pgvector.rs. So you could try that out. I haven't validated myself. You could also try and use a dense vector to store the sparse embeddings, but it turns out that's challenging too because there are limits on IVF flat. It will only allow you to apply the index to 2,000 dimensions, whereas the BERT tokenizer is over 30,000. So that becomes an issue as well. Now, in the advanced implementation, I actually set up BM25 not using vectors. I just store dictionaries of terms. And if you store dictionaries of terms, you can use more traditional indexes, like you can use binary search trees, and you can also use generalized inverted indexes, which are like at the back of the book. If you read a book, you'll have an index according to keywords. You'll see which pages those keywords are on. So that kind of index can be used and allow you to speed up the search. And that's something I'll do in the advanced implementation. Just a few last notes. I said that the BERT uncased tokenizer is how the dictionary words are defined using pgbestmatch. This is one approach to tokenize. I'm going to use a different approach in the advanced method. With the BERT uncased, it is insensitive to capitalization, which is good. There is some stemming, which means words like running are just truncated to run, so you get more matches, but it's not complete stemming. And there's no stop word removal, which means common words are not filtered out. It's good if you can filter out common words that are not very meaningful in terms of query match, because it reduces noise and that can improve performance. So with that, we'll move from the basic example on to the advanced inference repo example. Okay, so for the advanced approach, there are a few things I'm going to do differently. I'm going to do a faster BM25 implementation using a custom implementation for indexing. Sorry, I repeated myself there. But basically, we'll make it faster by using indexing. I'm going to use stemming and stop word handling to improve the search performance. I'll talk about how to extract text from documents and how to chunk it, including using binary search for generating the chunks efficiently. I'll use asynchronous database calls. This means you can hit the database in parallel, which allows for higher production throughputs. I'm going to do some speed and performance evaluation, and then I'll set up a simple command line interface that will allow us to run dense and sparse search on a body of text. And I'll upload more documents. I'll upload touch rugby rules, as you might expect, so we can do some queries on that. Now, just some little explainer before we go into the advanced inference repo. I mentioned a few things about dense versus sparse search and want to show you them again, just through a few slides. So a dense embedding. Here, I just want to talk about why the indexing needs to be different for both types. So in the dense case, where we've got embeddings for some text, the dense embeddings often look like this, or they might usually be floats, so they'll be decimals like that there. But the point is you have very few zeros. That's what makes them dense. And these are amenable to hierarchical clustering. There's often clusters that you can find, and that will work effectively to allow you to do a faster search through the clusters rather than brute force search through everything. Now, a sparse embedding looks more like this. You'll only have a few non-zero entries. And an example might be, let's say you have a dictionary, the house, apple, man, woman, shoe, house. But for your given document, you only have the word the, and here's a statistic for the, like maybe the inverse frequency. But you don't have the word house, apple, or man, but you do have the word woman. You don't have the words shoe, house, etc. So that's why the entries are often sparse when you're looking at keyword statistics. And these are less amenable to hierarchical clustering because there's just a ton of zeros and there aren't a ton of clusters. So what you do is you use something like IVF flat. This basically will group the sparse vectors according to each term. So if a given term is present, you can create a group of the documents that have that term. That's a simplified way of thinking about it. Now, if you have the sparse vector with zeros, you can pack it to be more efficient. I already mentioned this, but essentially you can just drop storing all the zeros and instead just store the non-zero entries. But the issue is sparse vectors, at least as defined in pgvector, they don't support IVF flat. So you can't easily apply that index that I described might be useful on them. So the workaround that we're going to employ here in the advanced approach is instead of storing the keyword statistics as vectors like this, we're going to store them in JSON-B format. JSON-B means binary JSON, which is an easily searchable form of JSON. And so we're going to store the vectors like this. So it's a dictionary. The has got a statistic, woman has got a statistic here. And note that this is a sparse form of storage because we're only going to store for each document the non-zeros. So we'll only store the terms that are actually present in that document. And once we have stored in this format, we can use indexing techniques like binary tree search in order to improve the search speed. Now, how does binary tree search work? You can just think of it as a form of sorting, for example, alphabetically of these terms. And so when we want to find a given term like woman, we don't need to compare the word woman with all of the words in the dictionary. We can just start off and we can have a search process that's going to be on the order of, I think it's log n instead of n, because we're going to use binary search and basically cut right to the middle. And then we'll start searching at the middle. And then if we don't find a match, we're going to cut within halfway of that midpoint and then halfway and then halfway. That's binary search. So you can cut down to the term much faster than brute force search through all of the index. And this is what's going to allow us to more quickly find terms that are relevant and speed up our query search for the BM25 approach. So just a few other notes on what I'll cover now in the advanced repo. I'm going to cover file upload, including chunking, command line search. I mentioned asynchronous calls. We're going to use indexing, hierarchical, navigable, small world on the dense vectors. I did that before, but we'll use it now. We're going to use binary tree and GIN, which is generalized inverted indexing for BM25 components. And we'll use text normalization and stemming for BM25. So I've cloned the advanced inference repo. this one here, and I've got it open in VS Code. Actually, this is still the basic one. So let's go to the advanced repo. And I'm just going to work down through this script. It's quite a bit longer as a script, and you'll see the different improvements I make. So the installation is very much the same. We're going to install Postgres. Actually, you don't need to install Rust because this is, we're not going to use PG Best Match. We're going to do a custom BM25 implementation. Then we will install PG Vector because we're going to use that. So this is very much the same as previously. And now is where things are going to start to diverge a little. So to create the database, we're going to do it in a more secure way. We're going to create some environment variables that define the database: user, password, name, host, and port, and we'll add those to a .env file. We'll additionally add a Nomic API key. If you go to Nomic Atlas, you can get an API key so you can hit the API to get embeddings instead of running them locally. And this can be a bit faster if you don't have a powerful machine. If you do have a powerful machine, it's probably faster to run the embeddings locally. So I've defined this env file, and using the env file, so I'm going to source those variables. I'm now, and let's just make sure I'm in the right folder. Yeah, Postgres RAG. I'm now going to drop the database from yesterday and create fresh a new user, create a password for the user, create a database, grant privileges to that user on the database, and then enable the PG Vector extension. So I've done all of that. Everything looks good. Don't worry about this. That's just because I've pasted in the comments as well here. On Ubuntu or Debian, the requests are a little bit different, and you can also get requests for Windows from ChatGPT. So next, we're going to set up the database contents. Now, I have the database set up, so I want to set up the structure of the database. And for that, I need to have a few Python packages installed. They're pretty much the same packages as what we used before, and they install very quickly with UV. And to get the database set up, we're going to use a series of migrations. So we're going to run first one migration to create the base table structure, then create the extensions and indices, and then to set up the BM25 functions, which is our text search. Now, those migrations are in the migrations folder. So let's take a quick look at these. The first one for database setup, we're going to have an ID for each chunk, the raw text. We're going to have some chunk metadata. This is a new field that I've added, and this allows me to assign a page number to every chunk I upload, or a line number if we're uploading a text document that doesn't have any pages. That's useful because when you retrieve a given chunk, you will know what page it is, and you can use that information in your UI to tell the user what page the chunk has been retrieved from. I have a column for the dense vector embedding, and then I have some timestamps. Now we're coming on to the BM25 and the custom implementation. I'm going to need to store some statistics for each term. So each term, we're going to have the number of documents it's contained in, and we're going to have the total occurrences of that term across all the documents. So the word zombie might be present 1,000 times across 50 documents. Next, we need a table for the statistics. So for a given document, we will have the ID of the document, the length of the document, because BM25 uses length normalization. That is, by the way, included in the basic repo. The length normalization is in general BM25, but I just use the default values for the length normalization hyperparameters. I'm going to use the default values here too. Then for each document, we're going to have the term dictionary stored as JSON-B. So I talked about that already in the slides, and the timestamp. Next, we're going to create what's called a materialized view. This is a derivative view that is beneficial for speeding up queries, and it's going to allow us to store a count of total documents and also the average length of the documents. Now we get to indexing, and indexing is what allows us to speed up the searches on the keyword statistics. And there are quite a few indexes that we can create here, some of which we're actually not going to use. For example, you can index the chunk metadata if you want to be able to search the chunks according to page number. We're going to add an index on the term statistics. This is simply indexing the terms as the back of a book would. The back of a book will usually have keywords, and say you pick a keyword, again, zombie, it'll say, oh, zombie is on page 35 and 57. So if you were looking for the pages for zombie, you can quickly know from the back of the book. And this is how this index here will work on the terms. It just tells us which chunks have a given term, which, speeds things up a lot in finding the right chunks if you know which term you're looking at from the query. We have another index here for the document statistics, the length, and timestamp based queries. Okay, so that was our initial database setup. Next, we want to set up the dense vectors. This is quite a short migration. All we're doing here is creating an index using the hierarchical navigable small world on the dense embeddings. And these are the hyperparameters. I'm just sticking with the standard. It's to do with the cluster sizing and scaling. So you could dig in further, but optimal values, probably just picking the defaults is fine. Now, the last migration script here is to do with our BM25 setup. It allows us to set up the statistics. So you'll remember we've defined the table structures here in the first migration, but now we actually need to run some operations to set up those statistics. Now, there are two types. There are two ways in which we're going to filter the text that comes in. The first is that we're going to remove common words or stop words. And the second is we're going to shorten the words down to their stems. And to do that, we need dictionaries for providing a list of potential stem words and also a dictionary for stop words. And that's what this is here. We've got a dictionary here for the stems called English Stem, and we've got a dictionary here called Simple Dict. So by effectively loading up these dictionaries, we're going to be able to remove the stop words and also reduce the words down to their stems. Now, the nice thing is we're doing all of this filtering in Postgres, which is going to be good for speed. So actually, all of the text cleaning or normalization, you can think of it as it's being done in Postgres with the setup that we're using here. So we've got a dictionary for stemming, we've got a dictionary for the stop word removal, and then here we're setting up a configuration. You can think of this as a pipeline. The pipeline is going to first remove stop words, and then it's going to reduce words down to their stems. Next, we're going to set up some BM25 functions. This is the formula that you use. This is how we calculate statistics. And if you look up the BM25 formula, you'll see that one of the pieces is the inverse document frequency. So you're looking at how frequent a word is in a given document versus across the whole document database. So, sorry, let me say that differently. Let me say that correctly. The inverse document frequency, it relates to how many documents have a term versus how many total documents are there. So if there are 3 documents of the word zombie versus the total number of documents, that means the term is fairly rare and it's something we should pay more attention to. So this is calculating the inverse document frequency, which itself is going to be used then in calculating the BM25 score. And you can see we're going to use that calculation of the inverse document frequency later on down here when we're summing up the contributions of every term towards the BM25 score. So next we have a function. This is the entire BM25 score calculation. We're defining the different data types that go into that, including the default values that are being used. There's a hyperparameter here that's for scaling the length normalization, and there's a hyperparameter that is used for scaling as well the term frequencies. So with all of these parameters set, we're able to calculate the numerator and the denominator of the BM25 score, and taking in the inverse document frequency. This is the total BM25 calculation. We've got a term for inverse document frequency. Then we have a numerator, which relates to the term frequency, and a length normalization. Which relates to the term frequency times hyperparameters. And then the denominator, which relates to the term frequency, hyperparameter, and the normalized length. So putting all this together, we have a BM25 score here. And then lastly, we've got a pretty long function here. We've got some table creation, but we've got a long function here that allows us to actually search. And the way we search is we take a query, we take each of the terms in that query, and for each term, we sum up the statistics in a given document. And then when we've got the summed statistics for each document, we can now sort which documents are most relevant according to those statistics. So that's what this is doing here. For example, you can see we're taking the query terms and we're parsing them using Postgres dictionary. TS parse is a Postgres native way of parsing. It's basically a dictionary defined by Postgres that allows us to split text into words. You can see we're skipping any spaces here. The space in this Postgres dictionary is number 12, word number 12. So we're going to skip that. We're also going to convert the text to lowercase so that we can get matches that are insensitive to case. Now you'll see as part of the processing, we also have this 2TS vector with simple conf. Simple conf, you'll remember from earlier, that's our configuration, our pipeline that's going to remove stop words and that's going to reduce the words to their stems. So all in all, this search here is going to allow us to process the query, then calculate the sum of statistics for a given document, and then select the most relevant documents. And we're going to select the most relevant limit val number of documents. So often we might want the most relevant 6 or 12, for example. Now, last of all, we have some functions to create statistics tables. We already defined in the first migration script the structure of these tables, and now we're just creating them. So we have tables for term stats, doc stats, and the global statistics across the documents. Now, BM25 does depend on all the documents in the database. So the statistics will change anytime you add a new entry into your documents. And that's why you need to refresh all of these statistics every time you do add in a new document. So with that, I've defined all of the migrations and I'm ready to run these migrations, which I can run here, and confirming that we have set up the tables, we've set up the dense embeddings, and we've set up the functions for the BM25 work as well. Now, the BM25 is all being calculated in Postgres functions, which is really nice from a speed perspective. But we're going to need a Python script to calculate the embeddings and then inject them into the database for every document that we have. And that is going to require a helper function that I've defined within the source folder, and then utils, embeddings. And then within embedder.py, we have a script that allows us to just create embeddings. It's like the script I showed you earlier in the basic repo, except it allows for creating embeddings either through the API or through a local model. So here we can just take a quick look at some of the functions. We have a nomic embedder. We're going to define whether we use the API or not. If we don't, then it's going to use a local model. It'll have a dimension associated, a maximum batch size. So we're further going to allow for batch processing. This will speed things up for document uploads. If you're uploading a lot of documents, if you're just doing one embedding at a time, it's going to be really slow to upload. So you want to parallelize that. Now, actually, the sentence transformer library will automatically parallelize if you're running locally, although you're limited by your computer's computing power. But if you're going to do remote querying, you need to set up a multi-thread querying process, and that's why I'm setting a max batch size here. I think you can actually directly hit the APIs for Nomic or OpenAI with a literal batch of data, not even using multi-threaded. So every batch you can have up to, I think it's maybe 100 for Nomic or 2000 for OpenAI. And then you can additionally parallelize on top of that by having a multi-threaded process. So you see some of the scripts here. We have API requests where we hit the correct model, we hit the Nomic endpoint, and then we also have a batch API request where I use threading to just increase the number of parallel requests that I'm making at one time. But otherwise, everything is the same as I described before. We have a task type that's going to define the prefix. Remember, you need to put the prefix of either document query or query before the text when you're going to embed it if you're using the Nomic embedder. If you're not using the Nomic embedder, then there's no prefixing. This is generally true, so a lot of embedders don't have any prefixing, but if they do, you would have to customize this to something else. Now, I'll note that there's a config file here that allows you to set these hyperparameters, or rather parameters. You need to set the embedding dimension, the model name, and the chunk size. These are the settings that you're going to use if you're using a local model. And Then if you're using the API, I currently have it set up only to support the nomic model. You could support another model like OpenAI. You would just have to change the code within that embedder script. This config file also allows you to load up the database with some default values, and it sets up the database URL. And it also allows you to print some connection info if you want. Now, the chunk size here is going to be for when we upload files. It's going to set a maximum size of the chunks, so we'll come to that a little bit later. Okay, so I think we can run this test script here. It's a script to do embeddings, and if you run it from main, it will just do an embedding of a single instance or a single example of text. I'm actually going to use the API, so I'll just set this to true. It's currently running without the API, but the next time we run it, it will use the API, which should be a little bit faster for embedding. Next, we're going to look at how to add data to the database. And I have two scripts for this that are manual. You can literally add some hard-coded data by using this create delete chunks. You can also delete chunks, and then you can add custom snippets of data by using this create delete chunks without the simple afterwards. And this will take actual chunks, embed them, and calculate the statistics. And then the next step is if you want to upload a document, you chunk it, and then you inject it. And that's going to be done by using some document processor scripts. But first, let's just go through the manual injection of text, and we'll take a look at this create delete chunk script. It's going to be very similar to the create delete chunk simple, except the simple script literally just adds hard-coded data, hard-coded embeddings, hard-coded statistics. So let me go to the create delete chunk script, which is present within the utils folder. And you can see that when we run this from main, it's going to try and write a new chunk. And it's going to do that by using the write chunk function. So let's take a look. And remember, we're using asynchronous calls here, so we can allow for higher processing. And in this case here, we're going to write in a hard-coded chunk. The capital of France is Paris. We're going to insert a document ID. We're going to embed that document using the embedding function from embedder. And then we'll just print out some info so you can see some info on the embeddings. We will add in some metadata. Here I'm just making up some random metadata, but usually we would put in something like page and then the page number here. That's if we're processing a file. We're going to convert to NumPy array for Postgres vector format, connect to the database, and then we're going to write the data into the database. So we write in a token term and count as frequency. We're going to parse the text using Postgres dictionary. Then we're going to calculate the doc length, get a JSON for the terms. This is the JSON-B that we need to have a terms dictionary. And then finally, we're going to insert into the document statistics and the term statistics here. I then have a function to read in the chunks that are present in the database. So you can see the process when we run this script is we will write a new chunk, we'll read the chunk back, and then I've created a simple script to allow us to delete some of the chunks. And this just allows us to delete entries from the database according to chunk ID, or to delete all of the entries. So let me just run this. That's the simple script. So yeah, you can see I've just entered some hard-coded values here. They're just random values. And I've just injected some hard-coded text. Let's just delete all of the entries in the database. And now we'll run the create delete chunk script. And you can see here, we've added in a chunk. The capital of France is Paris, which is the chunk I showed you earlier. It took about 20.22 seconds to get the embedding from the API. And then it took just milliseconds for the document insertion and the term processing. So yeah, it took just about 0.24 seconds for processing that. Then it reads back the content of the database, and then it allows us to delete chunks, and I will delete all of the chunks. Now let's inject two specific chunks about the capital of Ireland and the capital of France. So all of that is done, and we won't delete the chunks this time because now I want to run a search. So with the chunks injected, I'm able to do a dense search, which is using the meaning or semantic type search. And when I search for what is the capital of France, it's going to find that the most relevant chunk, according to the dense search, is the capital Francis Paris, which is good. And we can also run a sparse search. And you can see how fast the sparse search is, like 20 milliseconds. It finds that the most relevant chunk is the capital of Ireland, is Dublin, when I ask what is the capital of Ireland. So yeah, this seems to be working well. Let's just check out quickly how the search dense works and the search sparse. So when I call the search dense function, it's going to run the simple dense search function here, which takes in a query, the number of chunks to return, and an embedder. And it's going to just do, it should do cosine similarity. So let's scroll down and check. And indeed, this is the operator for cosine distance. So 1 minus distance is similarity. And it's going to then sort the rows. And note that it's going to return here the 2 closest rows according to cosine similarity. Now here we have the sparse search. And the sparse search, when we run from main, is going to run simple sparse search. It's going to take in a query, the number of chunks to return, defaulting to 1, and then the hyperparameters for BM25, which are the K1 value and the B value, which have to do with the term frequency hyperparameter and the length normalization hyperparameter. You can see we're also timing how long each of these steps take. And we connect to the database. So we fetch statistics. And then what we're going to do is we should be calculating the score. So yeah, in fact, the way this works is using our search documents BM25 function. So we've got a database function, and the way we run the search is by calling that function in the database with the required input arguments. So yeah, everything happens in the database, and we're going to get back the number of closest BM25 documents. So you can see now how we can inject arbitrary rows of text into the database, have them create dense and sparse, dense embeddings and sparse statistics, and then apply the indexes and allow for search. So our next step is now to do this for uploading full documents with a lot of text, which means we're going to have to chunk those documents. So next I'm going to take a look at how we chunk documents optimally and inject all that data into the database. Then we're going to be able to run searches on those documents and furthermore set up a command line interface for running searches. So for the document reading, we're going to have a utility called document reader, and you can find it in the document processor folder. And this is going to just read in a document, and that will ultimately be called by process documents. But let's take a look here at the document reader script. So it's going to take in a file path, if we call it from the command line, and then it's going to get chunks by using the read document function. So this is the key thing the script does, is create chunks, and it does so differently based on the document type. So if you have a PDF, there are naturally going to be pages, so you can chunk it by page, provided that the pages don't have more than the embedding limit. So if your embedding model has got a length of say 256, like say mini LM, then unfortunately you're not going to be able to just each page separately. You'll have to have chunks within each page. But if you use a larger model like Nomic, you can easily just have each page be one chunk, which is pretty nice. Now, if you have a text file, there's no such thing as pages. So you're going to have to make chunks based on the lines or the characters. The same for a markdown file. And for a Word document, you can chunk based on paragraphs. You probably could chunk based on pages as well. Or you can just chunk based on the number of characters and keep a constant number of characters or tokens per chunk. Now, there's a speed trade-off if you decide to count characters versus tokens. Tokenizers are going to be slower than just counting characters, but it's going to be more accurate in terms of chunk length, which means you're at lower risk of the embedding model truncating your chunks. So just be aware of that. One approach I like to take is just set a character limit or a word limit that's sufficiently small that you know it's very likely going to be within the tokenized limit of the embeddings model. And that way you can just use a word or character limit, which will be fast, but still make sure that you're generally underneath the size limit of the embedding model. Okay, so this read document function is going to start by checking if there's a PDF. If there is a PDF, it's going to go through on a page by page basis Now I do have a check that just in case there's more characters or words on the page than is allowed, it will split it into multiple chunks per page. And notice here how I create the metadata for each page. So it's going to tell me the source was a PDF, and then it's going to store the page. So every chunk is going to have a page assigned to it, and also will have the document type of PDF. Now, if we are within a page and we need to decide how many chunks to have, in that case, we're going to use binary search to figure out the optimal number of chunks. This is better than iteratively trying to design your chunks. So the most naive way you can create chunks is literally keep adding words until you hit the limit, which might be 8,000, and then stop, define the chunk, move on to the next chunk, keep adding words, define the chunk. But that involves a lot of operations to keep adding words till you hit the limit. And that's where using a binary search type approach can cut it down to kind of a log type time for creating, or log number of steps for creating those chunks. Just notice that if the length of the page, a single page, is below the chunk size, then we know we can just use the whole page as a chunk. So we just continue and we don't even bother with the binary search. So that's another speed up. Now, if you're using a text or markdown file, the approach to chunking is simply to create chunks of the ideal chunk size. And in this case here, you can see we're using a more naive type of chunking. This is the suboptimal one I mentioned earlier, where we're literally just adding on a new word every time. So you can see here to create a chunk that reaches the maximum limit. So really this could be replaced by a binary tree type search if you want to further optimize the time. Note that it's not that slow because these operations are just really fast. But if you really want to be optimal, you should move towards a binary tree type search up here. And so this is how reading the documents will work. I actually don't think here I've got docx included. If you want to support docx, you could do that by using the Python -docx package, and that will allow you to read in docx files. Maybe it's some functionality I'll just add in after the video because I think it's handy for quite a few people. So this is the read function. And if we run this for a given PDF in the data folder, so I've got my touch rugby rules. Let's see where. It's if I close the source, yeah, it's in the data folder here. You can see there's, I need to actually install PDF viewer. So I'll take a look at that later. But in the meantime, if I run this script here, what it does is just set up some chunks. And so you can see the start of the first two chunks here. This is the start of the first chunk and the start of the second chunk. And you can see each is being assigned its own page here. Now, we don't just want to create chunks. We want to actually get the embeddings for the chunks and inject the statistics. So for that, we're going to use the process documents function, or script rather. And that's available in the SRC, the source folder. And you can see all this script does is it will take in some arguments and run process documents, which itself is going to first run chunking with the read document function, and then it's going to process the chunks in batches. Now, you don't want to just be sending one chunk at a time to get embedded. You want to parallelize and get many embedded, and then you want to write a batch of chunks into the database. And so that's why we accumulate the chunks up as far as the batch size. Then we process the chunk, which means we're going to get the embeddings and write them to the database. So that's exactly what we're doing here. We're getting the embeddings and then writing them into the database and getting the term frequencies. So this is calculating the statistics that we need for BM25. So I can run this process documents, and this will now not just create chunks, but also actually write them into the database. And this is going to require us to call the embeddings model. So it takes a little bit of time, and then we'll be in a position to make queries to the database. So yeah, there are 24 chunks because there are 24 pages, and we've got one chunk per page because our embeddings model is big enough, and the document processing is now complete. So next, we are going to be able to run searches, and I'm going to use the same search dense and search sparse functions as I showed you earlier. So if we search dense for how much is a trolley worth, And if I just look at, you can see here, the top match includes a chunk with the phrase, a try is worth 1 point. So that's pretty good. So we've got 2 matches here, and actually the very first one, which has the highest score, has got the right phrase within it. And then if we do a sparse search, you can see really fast. Let's check. And yeah, the sparse search also is picking out the correct chunk with the most relevant phrase within it. So everything is working great here. Now that we have the ability to upload documents and run searches, we can create a command line interface that allows us to do queries. And yeah, this is just a script that allows me to run from command line either dense or sparse searches by calling those exact functions. And the easiest way to show you is just by running it. So I've run that script, and now I can type in dense and then my query, what's the try worth? And I can also add in how many chunks I want returned. So if I just want the top one, here you see it's returning the top one. And if I want a sparse search, I can just type in what's a try worth? And again, I mean, we can just default to 1 chunk and it returns 1 chunk here. And so that's your command line interface. And that wraps up everything for this more advanced implementation. You can see how I allow parallelization of embedding and creating stats for the documents, which allows you to upload documents faster. You can also see some of the optimizations around how I define the dictionary by removing stop words and then by stemming the words as well for improved performance. And then I use asynchronous calls to the databases in order to improve the throughput as well. So these are all some of the techniques I've used. Back right at the start of the video, I showed you assistant.trelis.com, that first app I built with the high latency. And you can see how fast it is using sparse search. I know this is a small database, but even as you upload more PDFs, you should be still getting good performance with this approach, getting some very quick sparse searches. And if we look at a dense search using the API for embedding, we're able to get back a result for that in just about half a second. If you couple that with a fast model from Cerebras or Groq, or a model like Llama 3.18b that's running fast on Fireworks, you should be able to get responses back within just a few seconds to your queries, including the retrieval. And that's it for this Postgres overview of how to build a retrieval system. I'll put a link to the resources below. The basic inference repo you can find publicly on GitHub under the Trelis Research Organization. Then you can get access to the advanced inference repo by heading over to trelis.com. I also have a section now on trelis.com website for enterprise requests if you are interested in getting more support and software for an enterprise type deployment of these kinds of solutions. In the meantime, any questions on this Postgres implementation, let me know below in the comments. Cheers.